All right, let's go ahead and get started with lecture 18 and try to get back to where we were last time before we left off. I think we had just finished covering the Kaiser window filter design method, which one of the motivations for that was we went through the window design method, but it didn't really give you more fine control over it. It was sort of like a guess and check method where you didn't get to set maybe you didn't get to necessarily set the attenuation maybe where you wanted it as easily, where the Kaiser window is kind of more based off the specs, and so it's a little bit cleaner because it's more of a closed form design. And I think we were about to do one of these since there's a homework problem where you actually do this. So let's do one just for fun all the way through, and we'll jump to MATLAB and just show you kind of how to go ahead and do it. And I think we had an example that we maybe didn't start yet. So for our example filter, first thing is to understand our requirements or our specs. So our pass band 0.4 pi, stop band 0.6 pi, and this delta factor, which corresponds to our attenuation, 0.001. So what does that mean that means that we're going to have some tolerance of ripple here, a transition band, and a tolerance of ripple there, where that ripple level is delta, and if this is 1, I guess the max of this ripple is 1 plus delta, and the minimum is 1 minus delta. So that kind of controls the passband ripple and the stop band attenuation. The passband was omega p, stop band omega s. So when we're done, we plot the frequency response in MATLAB. We hopefully will see something that looks like this. This is what we're shooting for. So the first thing to do is start converting these into the parameters we're going to use for the filter. So I think what we'll do is start with that. So we had some filter design equations last time. We're going to kind of race through those again, but this time put in these values. And then we'll go to MATLAB and plot it and make sure that we understand what it takes. So second step, let's go through our parameters. There were several intermediate constants and things that we had to calculate. One of them was called omega c, which is cutoff. And cutoff is kind of a loose term. In these filter problems, you've probably seen it with the Butterworth. It was where things just started to turn. Here it's kind of in the middle between the passband and the stop band. So you really need to know what you're talking about when you start throwing around words like cutoff, because they mean different things to different people. But for us, in the context of the Kaiser window, it's just the average between the passband and the stop band. And if we average 0.4 and 0.6 pi, we get 0.5 pi. So that's under control. Capital A, which stood for attenuation, was calculated as minus 20 log 10 of del, which is 0.001, or 1 times 10 to the minus 3. So log base 10 of 1 times 10 to the minus 3 is minus 3. Minus 3 times minus 20 plus 60. Now there was a kind of a bizarre formula that was related to curve fitting from last time based on the value of A. We were calculating a shape parameter. And I think I might write it down again just for context. But now we got to get the shape parameter. And beta was 1102 times A minus 8.7 if A was greater than 50. And that's our case for this example. And then it was 0.5842 times A minus 21 to the 0.4 plus, and hopefully I'm writing this 886 times A minus 21. And this was all for the case of A between 21 and 50. That's an A. And it was 0 if A was less than 21. So kind of a bizarre curve fit result. But for us, in this example, A is 60, so we need to use that formula. So for us, beta is going to be what, 60 minus 8.7. And using your calculators, use your calculator at home, hopefully you'll get 5.653. So this is the shape parameter that we need to use. So we've got those two. I think we just got a few parameters left. Our next order of business is a parameter called delta W. And that is simply the width of the transition band. So that is the stop band minus the pass band, which is 0.6, right, minus 0.4 0.4 pi, so we get 0.2 pi. That's the width of our transition band. Now these equations aren't necessarily straightforward. You remember it's kind of a recipe that we're following here. This shouldn't necessarily be intuitively obvious. So m is kind of related to the order of the filter. I think there's m plus 1 coefficients in the final FIR filter that we're going to create. So that's a pretty important number. And that is, what, a minus 8 all over 2.285 times this transition bandwidth. And even though that formula is somewhat abstruse, at least it makes intuitive sense, right? Because the wider this transition band, obviously the lower order filter. You don't need to do anything fast, so you don't need a high order filter. If this transition band is very narrow, you need a high order filter, so M will go up. So hopefully that kind of makes some intuitive sense to you. And so we got what, 2.285 times 0.2 pi. And if we crank all that through, I'm getting 36.2 for M. So we can't have a 36.2 order filter, right? So, so 37 it is. So M must be an integer, M equals 37. Got to be an integer. So what do we have left? We have another helpful parameter, alpha, which is m over 2. So that's going to be 37 over 2. So that'll be 18.5. So now it's time to gather all our pieces of information together. Put it into the equation. And I think last time I wrote out part of it so that our final desired h of n was equal to this hd of n, which is, that's that sine x over x sinc function based on the truncation, or based on the ideal filter response, times, I think we were calling w of n, which is the window. And this is the Bessel function. And so we're going to multiply those together in MATLAB. So you end up with, surprise, an ideal thing with a window on it, weighting it, truncating it and putting a taper on it, which is kind of what we talked about last time. So just to be clear and to go back on this, this window function had a kind of a funny format. What, 1 minus capital C to the 1/2, and that was for n between 0 and m, and 0 otherwise. And C was n minus alpha all over alpha, everything squared. And we'll just for completeness, we'll also toss in HD just so you can remember what the desired was. And then we'll put them all together. And that was what, sine of omega c n minus alpha all over pi of n minus alpha. And of course this whole thing is only defined between 0 and m. So we're going to end up defining these two functions, multiplying them together. And we'll do that in MATLAB, but first let's put it all on paper. And so our final answer, where omega c, remember that was the average, so that's sine, and that was the average of the stop band and pass band, which is 0.5 pi. We already defined n and alpha, and n goes between 0 and m, And alpha was that helpful 18.5, so put 18.5 in there. And the denominator is n minus 18.5. Now for the Bessel function part, that's the I0, which we'll mess with in MATLAB, times that shape factor, which was beta, which we said was what, 5.6? 5.65 is probably close enough. We'll go 1 minus c because c is kind of ugly to write. We'll put that in MATLAB. To the 1/2. And this was all over, I think I must have left it out, 5.65. I'm not sure I included it up here like I should have. Nope, I didn't. So let's go back. I omitted that this has a denominator. So this whole thing here is divided by I0 of beta. And I think I did it right last time on Wednesday of last week. But this whole thing has a denominator. So maybe just to be really clear, we'll write it one more time. So with no typos this time. I0 beta 1 minus c to the 1/2 all over I0 of beta. And 0 otherwise. So that's what we're going to try to stick into MATLAB and see what happens. So we've got those two. Let's see if I can bring up MATLAB here. PC. Okay, so what do we need? We said that beta, let's make a diary so you can see some of this later at your leisure. Today's what? October 29th. So for us, beta was 5.65. No problem there. Alpha was 18.5. N was what? 0, 1 to m. So let's say m equals 37, right? And then little n is 0, 1 to m. So we've got that. What else do we need for all this? We need c, right? So c is n minus alpha. This whole thing squared, but it had a denominator that was also squared, so that's another alpha squared. So now let's go ahead, and we know omega c was what, 0.5 times pi? All right, so we've got most of our equipment here. Let's go ahead and form each part individually, just so if you were doing this at home and you were trying to make sure you didn't make a mistake, you could troubleshoot it with ease. So HD is what? That's sine of omega c times n minus alpha all over pi times n minus alpha. HD. Now let's just plot HD to make sure nothing looks funny here. We know what that's supposed to look like. It's a sine x for x type shape. And there we go. So that looks plausible. I can believe that's a truncated sink. So the next part we'll call Wn, which is the Bessel function. It's 0th order and it's modified. So I looked up ahead of time what that is. MATLAB has its own built-in Bessel function, Bessel I. If you do a help on Bessel I, it tells you modified Bessel function of the first kind, which is what we need, where nu is the order. And nu doesn't need to be an integer, but for us it's always 0th order for these problems that we're working. So we can say this is Wn is Bessel I. And for us, we're always dealing with zeroth order, so nu is 0. That's the first argument. The second argument is everything else we've been talking about, which is b times 1 minus c. All that was raised to the 1/2. So kind of an ugly expression as an argument. But then, just for fun, we divide it by Bessel I, zeroth order, and what was the magic number? It was b again. And we can plot this just to make sure nothing funny is happening and I didn't make any mistakes. Does this look like a tapered window function? Let's check. And yes, that looks like your standard window taper. What does a window taper look like? It's very small values on the edge, large value in the center, and a smooth progression down to the edges. So that's what a window is supposed to look like, and that looks like a window. So let's go ahead and say h of n is w of n times hd. And we can look at that just for fun. Make sure that element by element multiplication didn't go awry. And so it looks very similar to the other thing that we had before, except now, notice how on the edges here it's been attenuated. Why? Because we multiplied it with the window. So, of course, that's what you'd expect. We weighted these edges with the small value from the window function, so it smashed them down. So everything is okay so far. So now let's use MATLAB's built-in freqz command we talked about last time. So Hn is the b coefficients, or the coefficients that describe the zeros of the polynomial of the system function. There are no a coefficients, so we just put 1. And let's get 1,000 samples out. And let's see, WW divided by pi, because that's frequency from minus pi to pi, so now it's minus 1 to 1. And we want it in terms of power, so 20 log 10 abs Hej omega. So let's take a look at this and see if it makes sense. And is it visible from there? Might be. I'll make it a little bit larger in case it's hard to see. See if that cleans it up a bit. Might be a little bit better. So what are we looking for? We are looking for our specs of a pass band of what? So the pass band was 0.4 pi and the stop band is 0.6 pi. So since I normalized this by pi, 0.4 and 0.6 is where the action is. So let's sort of blow this up and take a look at it. So at 0.4, what sort of attenuation are we sitting at? Almost 0, so as much as I can see, we've got it controlled. There's no attenuation for any signals that we care about from 0 to 0.4 pi. So let's reset. Take a look at 0.6 pi. That's the stop band. What's going on there? Well, we wanted to get 60 dB of attenuation, and as we blow this up and get closer and closer to 0.6, what do we see? Well, it's really close. Right at 0.6, we're at, what, minus 62, 63, we're somewhere in here, which is good. We don't want to overdo it. So it worked pretty much like what you'd expect, or what you'd hope. And I think we advertised that m would only be within plus or minus 2. So maybe you could shave off a few coefficients if you wanted and still meet your requirement. But I think you probably get the idea there. I think the next part is for homework 6, which I posted. I want people to be able to plot the spectrums in kind of a certain way. And you might as well use the built-in FFT function at this point, because we're going to spend this lecture, most of this lecture and the next, talking about what it means to do an FFT and its significance. Basically, the user's manual for the FFT, maybe, or the DFT, more precisely. So let's talk a little bit about how I want you to plot the spectrums for homework 6. I have instructions on there, but I want to go through sort of an example so we can all get on the same page. And the reason we're covering this is so everybody can do homework 6 without any problems. So over the next few lectures, we're going to talk about the discrete Fourier transform, which is implemented in MATLAB using the FFT function, because an FFT is just an efficient implementation of a DFT, and the DFT is what we're talking about. So in contrast to the DFT, let's go harken back to chapter 2, where we talked about this, the DTFT. So there's our friendly DTFT. And when we look at it, well, this was a continuous function. Continuous, easy for me to write, continuous. And this was a discrete. And of course we could go back and forth, and we did, rarely, but we did, by integrating the spectrum, and that was e to the plus j omega n d omega. So we had this relationship. Well, these are very different functions from each other. One is continuous, one is discrete, discrete, continuous. So those are our relationships. Now let's put that in contrast to DFT, which is just discrete Fourier transform. And why is it called discrete Fourier transform? Because both the frequency and the time representations that we'll talk about are in discrete time. There is no continuous functions here. Whereas this one was called the discrete time Fourier transform because only the time part was discrete. The other part was continuous. Here we've jettisoned all that continuous stuff and everything is discrete. So when I talk about kind of the output spectrums, I'm going to use X with a index of k to kind of say, yeah, we're talking about the frequency domain, because since everything's discrete, you're not going to know what I'm talking about, right? I mean, x could be anything. So when I index x with a k, I'm talking about the frequency domain, because otherwise it can quickly get confusing. And that's e to the minus j 2 pi n k over cap n. But then we can go backwards. Of course, k goes 0 to n minus 1. Of course, we can also go backwards. I'm going to try to make my x larger when it's frequency, but I won't claim that I'm always able to do that. So we'll go k equals 0 to n minus 1. And now e to the plus j 2 pi n k over cap n. And n equals 0, 1, dot, 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 n minus 1. So those are our two kind of our analysis and synthesis equations that we're going to be talking about during this lecture and the next one. But the reason we're getting into it now is that I want to be able to talk about how to plot things in MATLAB in a convenient way. So what's important about this? This is discrete and that's discrete. Everything is discrete. So one thing you can probably notice quite right off the bat, that if x of n is a sequence such that, and this is not an extremely rare occurrence or anything, xn, I'm just going to say xn is xn. A is A, right? And 0 otherwise. If that's the case, which seems kind of like a tautology and very benign, then there's a nice relationship, which I hope is relatively intuitive, between the DTFT and our new, or probably not new to most of you, discrete Fourier transform frequency sequence. It's just the DTFT sampled 2 pi k over cap n, where k is 0, 1, dot, 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 n minus 1. So this is really just samples of the continuous stuff that we know and love. Now, for several reasons, and I'm going to try to show some examples today, we will sometimes, it makes a nicer, cleaner plot if we, in a sense, zero pad or, I guess, make these frequency samples finer, kind of interpolate in frequency. So how is that done? And we'll show how to do it in MATLAB in just a second. And that is xn again, e to the minus j 2 pi nk all over nFFT, where nFFT is the number of frequency samples out. So this is kind of useful for making a nicer plot. And at the end of the course, when we talk about spectrum estimation, you'll see why it gives you better information many times. In our case, nFFT is an interpolated version of the frequency spectrum. And so nFFT is usually much greater than n. I think we're going to do several examples of this to try to make it pretty clear what we're doing, or at least how to do it. So typically we're going to look at it, but an FFT is an efficient implementation of a DFT, discrete Fourier transform. That's all it is. And so it doesn't mean one algorithm, it doesn't mean one type of algorithm. In fact, there are many toolboxes out there, like, have you heard of FFTW, fastest Fourier transform in the West? It's sort of a joke, but basically it's a bunch of algorithms that are designed so when you give it a certain size FFT and you tell it what hardware you're on, it basically creates an algorithm custom for your set of FFT sizes and hardware. And so it's, stuff can get fairly sophisticated if you really want to go fast. So we're just going to be talking about later radix 2 FFTs, a family of algorithms, but in general, an FFT is just an efficient implementation, which we're going to use for plotting here. And I think the other part is the FFT shift command in MATLAB. Has anybody used that before for plotting spectrums? FFT shift basically swaps halves of data. So the zero frequency will be in the center. So you'll have a spectrum that has negative frequency content here, 0 there, and positive here. It's basically to help you make those friendly looking plots, because when we use the FFT function in MATLAB, guess what? It doesn't come out this way. When you use the FFT function, it basically comes out positive frequencies up to plus and minus pi, and then back down to 0 on both sides. So this is how it comes out. So this is where 0 is without using FFT shift. If we use FFT shift, it comes out in the center. And that sort of makes a nicer plot so we can understand what's going on. Low frequencies are always in the middle. High frequencies are to the edge. We've been talking about that the entire time. Hopefully that part's not confusing. You might think, well, why on earth do they do it that way? Well, it turns out that it's efficient to kick it out that way, so they do it that way. So we're going to use FFT shift to make our lives easier for plotting purposes. So I think we'll try to do, if I can, we'll try to go to the chart here and do some examples. Since we already have n defined, I'm just going to make up something. Like y of n is cosine 0.2 times pi times n. So if we look at that, what do we have? It better look like a cosine, right? Regular sampled cosine looks good. Now I'm going to get the FFT out, just so you can kind of see it. So now figure plot 20 times log 10 abs of yn FFT. So there we go. Now I don't have any frequency variable assigned to it. Well, the good news is, what do we see here? We see two peaks, which is good because that's what we got to see. It's a cosine. And we want to see those at 0.2 and minus 0.2 pi. Hopefully that's what we're looking for. Now I didn't plot it against any frequency axis. So what do we see here? Pretty much no frequency information. It's just 37 things out, 37 inputs, 37 outputs. Or maybe it's 38, because n was 38 or 37. So anyway, we've got our spectrum, but how do we interpret the frequency axis? Well, it turns out, like I said, the MATLAB frequency axis kind of spits it out, not the way we'd like it. So we're going to use FFT shift to plot it. Now this might be, we still don't have the frequency axis information on here, but hopefully it's a little more clear to you that, okay, we dialed in 0.2 pi, it better not be on the edges, right? If we're saying that this is zero frequency or DC, then we need to have things on the edges. Things need to be close, right? Out here is plus and minus pi. Now I guess the second part of this is, let's see, n what was it, who's in? Yeah, 38. So let's make a frequency axis variable that goes from minus pi, right, in steps of, what is that? That's 38. So I have 2 pi, minus pi to pi. I'm dividing it into 38 chunks, right? And what do I want to go to? I have minus pi on this side, but plus pi and minus pi are the exact same. So I don't want to go that far. I want to go to pi minus 2 times pi over 38. There's my frequency variable. Whose W? Better be 38. It is. So now let's try again to plot this. And put a W up here. And divide it by pi because we like things in increments of pi, right? And let's get a grid on this thing. I cannot see it. So hopefully if we look at this, we're seeing things close to minus 0.2 pi and plus 0.2 pi. And it's a little bit off, it looks like. Just a little bit, but it's pretty close to 0.2 minus 0.2. Now that brings us to the, wouldn't it be nicer if we had finer frequency sampling? Notice that the samples aren't sampled all that frequent. We have some samples, but what if we wanted to have a lot more? So just for giggles, let's hold that on and start over and interpolate the frequency spectrum. So let's use 1024 samples just for giggles, right? And then we'll have omega, we'll make this omega n FFT, and that'll be minus pi, 2 times pi over n FFT. And I'm saving all this in a diary so you can hopefully use it for your purposes for doing the homework. So who's on WNFFT? Better be 1024 it is. All right. Now, if we look at help on this FFT does it give you, it tells you this the discrete Fourier transform of vector x and some blah blah blah, and then it comes down here and says n is the endpoint FFT padded with zeros if it has less than n points and truncated if it has more. Well, the padding with zeros is the when you pad it the sequence with zeros, it basically interpolates the frequency spectrum, so you end up with more samples. And I think we'll get into that a little later. You just take it for take my word for it for now, and we're going to get into it a little bit further with frequency when we get into frequency estimation a little bit later in the course. So let's do that. Yn in FFT, and we'll just make that 20 log 10 abs FFT shift. I like that, FFT shift. Then abs, then FFT, then y of n, then FFT. So I'm giving it that argument in FFT. So the output will be 1024 and interpolated. All right. And we got to shift it, and we got to take 20 log abs. Now let's go back to our original and hold that on, and then plot. Do I have a variable for that? I do. And let's put it in red just so you can kind of see the differences. I think the grid's already on. And, oh. You know what I did? You see what I did wrong? Yeah. Notice Wn, I did not scale it by pi. Scale the other one by pi. Now it's kind of hard to see them both. I think you can see them. So now you can see more of the side lobe structure and how the side lobes go down, and also if we drill down on this, you can see this peak when we interpolated with 1024 equally spaced samples is a lot closer to the minus 0.2, which you'd expect, right? So that's one of the advantages, kind of stealing my own thunder for later in the course, of why you'd want to interpolate these things. So we get plus and minus 0.2, and yay verily, this 0.2 looks a lot closer on the interpolated spectrum. So when turning in these plots, that'd be the right answer. And we can even play with that right now, because what did we do? We defined h of n. Didn't we? Yeah, we defined h of n. Well, we can go ahead and take, let's see if dare I do that. Here's our original spectrum from MATLAB's Freak Z, right? But we can do our own. We can say, you know, Kaiser window, frequency spectrum. I don't know how to, Kaiser window filter or something. Trying to come up with a good variable. Spectrum. That's long enough for us. And that was NFFT, right? Let's go back to our plot from MATLAB. Hold that on. And see, do we even close? And it looks like they're kind of on top of each other, I think. Let's see. Yep. So you can see either way, you can get pretty much same answer. So hopefully that will help you a little bit, at least with the mechanics of plotting and seeing what's going on. And I put that simple example of cosine 0.2 pi in there so you can play with it, because I think part of the assignment 6 may have things like that in there. So let's see, did we cover everything? Let's see, maybe that wasn't real clear about FFT shift. So suppose I had a vector. I just wanted to make it real clear. 1, 2, 3, 4, 5, 6. All it does is swap it. You see where now 1, 2, 3 is over on the left side and 4, 5, 6 is there. And the whole purpose of that was if these were samples of a spectrum and frequency, now all of a sudden 4, 5, 6, which turns out to be 0 and low frequencies on 3 and 4 now, or I guess in 6 and 1, which were low frequencies, are now put together. So by swapping that, it makes it easier to plot. Now we don't have to do it that way. You can still see some people don't do it that way, but our textbook seems to do it so that low frequencies are in the center, and I think that's easier to understand for the most part. Okay, is there any questions about plotting anything in MATLAB? So we'll go back to the pad and try to finish up our discussion. Okay, that was 10, so now we're at 11. So now we're done with filter designs, and now we're going to talk about, like I promised, discrete Fourier transform. So now we're in Chapter 8. So this is Chapter 8 material, the DFT. And so we're going to get into kind of the technical details of the DFT, what it actually is, and how it's used. DFT, to me, is less of an algorithm and more of a process, and sort of a gentleman's agreement to use the discrete Fourier series in a certain way for signals that are not periodic. And so we're going to get into the details and kind of see what's going on under the hood, because if you do that, then you can kind of use the Fourier transform in different ways to accomplish your objectives in less of a black box. Like you can take advantage of the aliasing that you will get, as we will talk about aliasing a little bit further in the course, because you understand what the DFT is doing and you can understand how to handle it. So let's talk about the outline, because we're going to do some derivations of a few things, and I want to try to set the stage and organize what we're doing so it kind of flows. So the first thing we're going to talk about is the Fourier series coefficients. Of periodic sequences. And the reason we're going to do that is because the Fourier series coefficients turns out to be the outputs of the frequency samples of the DFT. That's the bottom line. Now, we don't call it that for maybe historical reasons, or I'm not sure why, but we're going to talk about the Fourier series coefficients of periodic sequences because that basically is the DFT. And it turns out because the Fourier series coefficients are supposed to only apply to periodic sequences, but we're going to cheat and apply them to non-periodic, and that's basically called using the DFT. So if that's so useful, then how can we get periodic sequences that are of any use? Well, basically we're going to construct periodic sequences. So these periodic sequences can be constructed. We can kind of make them up from finite length sequences, or from copies of finite length sequences. You can imagine just taking a copy paste and putting a whole bunch of finite length sequences together and say, okay, now it's periodic. It goes on forever in both directions. Well, the Fourier series coefficients, or the Fourier series of a periodic sequence, the Fourier series coefficients, a lot of words here, of a periodic sequence, correspond, which is a fancy word for R, the basically periodic sequence corresponds to the DFT of a finite length sequence. And it may seem like, well, why are we going to all this trouble just to go through all the math on this? And mainly is because this highlights the periodicity of the DFT. And why is that important? Well, it's important because if you're going to efficiently implement any of the things we talked about with these filters, you're going to end up doing it by implementing using FFTs, is the bottom line, or some kind of FFT processing. Or we're going to explain why you're going to do that. But what size FFT? The bigger the FFT, the worse off you are. That's more processing. So you want to do it the minimum that you can get away with for your particular application. And you're not going to understand how to do that unless you understand the periodicity of the DFT. So that's why we're kind of going through all this. You won't be able to implement things efficiently unless you understand when aliasing occurs, because that's where we're going with all this. So to start off, we're going to take a look at our Fourier series. So let's begin with the Fourier series. Just sort of a reminder of how that worked. And so we'll start with continuous time and work our way to discrete. So for a periodic function, FFT, which is continuous, we had a certain form for the Fourier coefficient. So we could rewrite this FFT, a continuous function of time, as AV, A sub v plus, and this was the kind of the Fourier coefficients part. That's what, cosine? And the b's were sine. And so maybe that's not clear, but this whole thing has an infinite number of harmonics. And so n goes to infinity. And so what was it? AV, BN, AN are the Fourier coefficients. And omega naught is just 2 pi over t. So you see this is some fundamental frequency, and we simply increase it an infinite amount. So we can think of this as, okay, we've got an infinite number of sines and cosines, or frequencies, to represent f of t. So let's take a look at discrete time. What's going on there? So if we go to discrete time, let's let, we'll call this x tilde of n, where we use this tilde on top of a variable to mean periodic. So xn is, it's going to be a periodic sequence. And so what does that mean? Well, it means that at some point you get the same answers repeating over and over again. So once you get past n, it repeats. So it's a periodic sequence with period n samples. Now we're going to say, well, we can probably represent this thing as also a sum of harmonics as well. So what's good for the goose is good for the gander, right? We'll go ahead and say, well, let's sum them all up with a whole bunch of e to the j 2 pi nk in cap n, where these guys here are our Fourier coefficients. I've kind of tipped my hand here by putting a tilde on top of this, as if it's periodic. But let's test that out and say, well, how many k's are there? So let's do a thought experiment and kind of lead the witness here, but let's let k equal k plus L times n, where L is just another index that can go on infinitely. And we're doing that just to see that how many k's does it take to represent the signal. So let's go back and look at this kernel under that constraint, where we have what, 2 pi n k plus L cap n all divided by n. Well, if we look at it that way, it's just e to the j 2 pi n k over n, 2 pi n k over cap n, and I'll break out the e to the j 2 pi n ln over n. Well, the cap n's cancel, right? So that just leaves me with 2 pi n l. Well, now you can see there's kind of a redundancy there, right? This is going to always be 1. For integers n and l. So by kind of expanding this out, we can see that, well, every time we add an integer l here, that just meant we skipped ahead by n. So this whole sequence basically is periodic with period n, because every time we add some factor of L times n to it, it repeats. Hence, kind of cheated and put that up there first. So our bottom line here is that basically for values of k, separated by n, that complex exponential is the same. So this kernel, that kernel wraps back around. So our conclusion is that there are only n. So one difference we're automatically coming up with is there's only n values, not infinite. There's only n distinct complex exponentials. With the harmonic, a lot of words there, 2 pi over n. So instead of infinite, now we're down to n when we try to go into discrete time. So now we're going to update our synthesis equation, where before we were saying, there's k's an index and it's going to something, we're not sure. Now we're going to clamp it off and say, nope, we're done after n. So we can now write our synthesis equation, 1 over n, and now k is only giving us n distinct values. And we're back to what, e to the j 2 pi n k over n. And that's our synthesis equation. Now our analysis equation, so we'll put synthesis, synthesizing our time sequence from our frequency samples, our Fourier coefficients. We can also get our Fourier coefficients from our analysis equation, which the book goes through a derivation of how to get this basically from the equation above. I'm not sure I'm going to take the time to do that this time. But if you want to see the derivation of this analysis equation, it follows from the one above with some mathematical manipulations. So it turns out they're both periodic, both the Fourier series coefficients, and of course we started with the premise that our input sequence was periodic. So what are we saying? We started with this, and we have to end up with this is periodic. And so with that relationship in mind, they're both periodic and they're both Fourier related. We're going to call them the Fourier series relationship. So discrete Fourier series, or DFS. So both these are periodic with period n, and we've got our relationship. Now there's some special properties that these sequences have that we haven't seen before in any other of our adventures, I guess, with playing with Fourier transforms, or discrete time Fourier transforms. And it's because of the similarities of these signals. And it turned out that previously there was no, property called duality for the DTFT. And why is that? Well, for the DTFT, xn was not periodic, and it was discrete. And remember x e to the j omega, that was periodic, period 2 pi, right? And it was continuous. So, as I mentioned before, these are very different animals, and there is no duality property. So what is, well, before we get into duality, what exactly duality is, if we look at the, well, we're talking about the discrete Fourier series. X tilde of n is periodic and discrete, and x of k is also periodic and discrete. And so that means there's a special relationship, or there could be a special relationship, which there is, between these functions in terms of their discrete Fourier series. So what is that relationship? And so for this DTFT, there is no duality, but for the DFS, there is. So the duality relationship is if you have a pair, and that's discrete Fourier series pair, and that's x tilde k. We've got that relationship. You have a pair. Then what would happen if you pretended that these Fourier series coefficients were not Fourier series coefficients, but just another regular time sequence, and took their discrete Fourier series? Well, you can do that. And when I treat the discrete Fourier series coefficients as just another time sequence, I'm going to use n here to try to communicate that to you. So I took these x of k's and I just rewrote it x of n because I'm treating them like a time sequence. And if I take the discrete Fourier series of those, what do I get back? N times sort of a time reversed version of the input. So you can kind of see how it's it kind of goes in a circle in some way. So what is this? This is the original input sequence, kind of in a time reversed order, modulo n, which we'll get to in a second, multiplied by n. Hence the big N there. So to try to fix ideas and make this somewhat clear, let's do an example that might be a little out there. So let's suppose we have xn, and it is periodic but I'm only going to give you the first, I guess that's sort of like the principal period, where n goes from 0, 1, 2, 3, you get these four numbers, but of course it's infinitely extent afterward and before. So if we get the discrete Fourier series for that, it's also going to be infinitely extended both directions, and I'll give you the principal period for that one. And this is for k equal to 0, 1, 2, and 3. So if given this, we can compute this. And now the question is going to be, given all that, let's use duality. So use duality to get the discrete Fourier series for the sequence (10 minus 2 plus j minus 2 minus 2 minus 2j). And we have to assume, or we have to say that it's periodic for this to work, right? Because we're getting the discrete Fourier series, which applies to periodic sequences. So using duality, we know how to do this, at least in theory, because we're given x of n, we know x of k, and this sequence here is, well, how about that? It is the x of k sequence, minus 2 plus 2j minus 2 minus 2 minus 2j, so we've got it all there. So it's just a simple matter of need to find n times, this is what, kind of a minus k or minus n. I think I'd like to write that as x of minus n. So we need to find that product n times x. Whoops, I'll get on the screen, it might be easier. So we need to find n times x minus n. And how hard can that be? Well, if you've done this before, you know that it's not necessarily hard, but it's easy to go astray. So what's our first, I guess, kind of rule of the road? Sequences are periodic. So everything is modulo n. Star, star, star around it. Everything is modulo n. The sequences are periodic, so everything is modulo n. Well, what does that mean? That means the entire universe of everything we deal with must be mapped between 0 and n minus 1. And in our example, 1, 2, 3, 4. So for our example, n equals 4. So everything has to be mapped between 0 and 3, right? 0, 1, 2, 3, since n is 4. Well, why is that troubling to some of us? Well, we said x of minus n, so that would imply minus 1, minus 2, minus 3, minus 4, or minus 1, 2, minus 2, minus 3, right? Well, we can't have that. We've got to have, everything has to be mapped, like I said, into this area. That's what modulo n means. So to kind of show you how to do that, there are probably multiple ways. I like to use a chart to kind of keep things organized. So let's start with our sequence as one column. And let's see. xk. Right. So I want to be able to get x of minus k. So we'll start with just x of k, or x of n. I guess it doesn't matter. Maybe we should make it x of n. Might make it clearer. That's a good point. Let's make that x of n. So what am I trying to find here? I'm trying to find x tilde of minus n. Well, I have x tilde of n. 1, 2, 3, 4. So I'm going to write that down. And those correspond to what? N equals 0, 1, 2, 3. Right? So far, so good. Well, what's minus n? Well, minus 0, that's just 0. But now I've got minus 1, minus 2, minus 3. Now I've got a modulo in this, which the book writes like this, double parenthesis n. So that's one way to write it, or you can write minus n modulo 4, because capital N equals 4 in our example. So how do we do that? We have to map everything in the world between 0 and n minus 1. We do that by adding or subtracting capital N. So is 0 between 0 and 3? It is. So 0 modulo 4 is 0. No problem. Minus 1 modulo 4, well, minus 1 does not lie between 0 and 3. So we have to add n to it, which n is 4. So we add 4 to it, and we get 3. Well, is 3 between 0 and 3? It is. So we're good to go. So we can add 4 to this. We can add 4 to that. Now, if these numbers were larger, we might have to add 4 multiple times. Or if these numbers were larger than 4, we might have to subtract 4. But for the examples that we're doing, this is kind of the case. So what is x tilde of minus n? Well, this minus n index is really these numbers here, 0, 3, 2, 1, right? Because we had to map this into these. All right, so minus n, so the first one is 0. So x of 0 minus n is 0, which is 0. So I go look it up, it's just 1. Xn of minus 1 is really the third index. So I go over here and say, where's the third index? It's here. So that's 4. So there might be an easier way to keep track of it, but I kind of like to do it this way. So minus n is now minus 2, which maps to 2. I can come over here and find a 2 and say, oh, that's 3. And for our final minus 3, that maps to the index 1. There's index 1. There's x of n, it's 2. So there's our modulo, our negative n modulo 4 version of the sequence. So now all we have to do is multiply 4 times that. So n times x tilde of minus n. Let's see, hopefully that's all on there. 4 times what? 1, 4, 3, 2. So that's what? 4, 16, 12, 8. So summarizing all this, let's put it all on one page. 1, 2, 3, 4. If we take the discrete Fourier series, we end up with 10 minus 2 plus 2j minus 2 minus 2 minus 2j. And if we take the discrete Fourier series of this, we end up with 4, 16, 12, 8. Now, I think sometimes people might get confused because what might appear to be a little bit magical is, all right, you did some stuff on a slide and we ended up with this, but we didn't even start with this sequence at all. We just ignored that sequence in computing this one. We went over here and messed around with this and ended up with that. And that's because of this duality relationship. And that might seem a little mysterious, but if we go back to slide 15 and and we look at these relationships, there's really a lot of similarity here, right? I mean, there's a negative sign in the kernel, but these two equations are very similar. And so it might not seem totally crazy that it sort of seems like we're doing a very similar operation over and over again, right? We start with x of n, let's say, get the Fourier series by this summation times a complex kernel. Then we took this and multiplied it times the complex kernel, did some summation, we got that. So it shouldn't be totally amazing that we can start with this, get the discrete Fourier series and go here, and then take the discrete Fourier series of this and get back to here, kind of referencing that sequence, right? That's what we did. We took the negative modulo 4 version and then simply multiplied by n. So that's an example of duality. And I think you can even play with it in MATLAB. If I steal my thunder from the later things, what is the discrete Fourier series? It's the discrete Fourier transform outputs are the same thing. Now I think we have 6 minutes left, and the next topic is periodic convolution, where we're really going to use this concept of delaying things and taking the negative, reindexing it like x of minus n in the modulo format. So I think this is a good place to stop, and we'll pick that up next time.